Welcome to day 22 of the 2024 Advent of Code. For today's problem, we are working with some monkey stock exchange, and the historians have spent some time deciphering the secrets of these monkeys and discovered that the buyers on the market seem to use random prices, but they're actually pseudo-random. Pseudo-random number generation is a form of number generator that basically deterministically generates bits in a way that appears to be random. So a lot of things use this. For example, a lot of video games use pseudo-random number generators, and in certain video games like Minecraft, people have found ways to manipulate this because it is technically deterministic. And so knowing the algorithm for a pseudo-random number generator lets you predict what it will generate next. So this is as opposed to true randomness. For example, an interesting case of this is Cloudflare, which is a tech company that requires cryptographically secure randomness, and one way of obtaining this is to have true randomness. So they actually have a wall of lava lamps and just point a camera at it, and their form of randomness is literally just by seeing what's on the camera. And you can actually visit this if you go to the Cloudflare headquarters, and they'll even let you walk in front of the camera because if people walk in front of it, that introduces more randomness. So that's a pretty cool example of true randomness, but here we have pseudo randomness. Each buyer starts with a secret number and produces a pseudo-random sequence starting from that. So given a secret number, the next number is determined by the following steps. We multiply the current number by 64, then mix it into the secret number, and then prune the secret number. So this changes the secret number once. Then we divide the secret number by 32, round that down to the nearest integer, mix it, and prune it again. And finally, we take this new secret number, multiply it by 2048, mix it, and prune it again. And this three-step sequence gives us our next secret number in the pseudo-random sequence. Mixing and pruning I initially thought would be kind of complicated. They're actually not at all. Mixing is literally just the bitwise XOR process, and pruning is just modulo by some number. So, in case you are not familiar with bitwise XOR, let me introduce it briefly. So the binary number system is how computers represent numbers, and bitwise operations refer to treating the numbers as bits, which is its binary representation. So if we look at the number 11, for example, that's in base 10, meaning that this place value is 1 and this place value is 10. Basically, as we move to the left, each subsequent digit gets 10 times more valuable. If we want to write this in base 2, we will use the digits as only 0 and 1. Just like in base 10, you can only have digits 0 through 9. In base 2, you can only have digits 0 through 1. And each place value gets twice as valuable every time you move to the left. So 11 would be represented as 1011 because that's 1 plus 2 plus 8. 13 would be represented as 1101 in base 2 because that's 8 plus 4 plus 1. So if we take 11x or 13, we line up the bits on the right side, like so, and then we take the XOR of each column. The XOR of two numbers, or rather two Boolean values, tells us whether or not either but not both of them are the case. It stands for exclusive OR. So for example, this case is false because neither of these are true, so the OR fails. This case is also false because both of them are true, so the exclusive case fails. So for these two, we would get a 1 because it is exclusive, and either this is true or this is true. So taking the XOR of 11 and 13 would give us a value of 6. This is represented in most programming languages as the caret symbol, including in Python. So this is pretty straightforward. So let's make our step function. It'll take a secret number and produce the next one. So we take the number and we multiply by 64, mix that into the current number, and then take that all modulo this value here. That's the new number. Then we do the same, but instead with dividing by 32. And then we do the same, but with multiplying by 2048. Now, each buyer has a different initial secret number, but our historian has uncovered the initial secret number of each buyer, which is our puzzle input. So, for example, given these four numbers, we will obtain this number after 2,000 generations. So let's just double check if this works. If we start with a number of 1, 2, 3, we see that we get this number here. So this step function appears to work correctly. So now we just need to determine the 2,000th secret number after this, and we get the sum of each of the 2,000th secret numbers generated by each buyer. So we can start a total for each line in the input. We're going to convert it to an integer, and then 2,000 times we will turn the number into the next number in the sequence, and finally we'll aggregate all of those into the total to get our answer for part 1, which takes a bit of time just because we have a significant number of inputs, and there isn't a great way to do this other than to just do all of the calculations. Now, I believe there might be a way to actually condense this step and optimize it mathematically. I'm assuming this is a power of 2. Wrong way around. Yeah, it's 2 to the power of 24. And so if you're familiar with bitwise math, I won't bother explaining this in this video, but this is just, these two are both left shift operators, and this is a right shift, and this is a Boolean, this is a bitwise AND because it's a modulo of a power of 24. So I believe you can condense all of these steps in a way mathematically that allows you to not loop 2,000 times, but the time spent figuring this out would not really be worth it. I'll actually do this at the end of this video just for the sake of interest, but under actual time pressure from this contest, there's no reason to bother trying. You would only save like 5 seconds. Now, looking at this part, I was expecting it to be a reverse engineering problem where we'd actually have to use this property to try to, for example, figure out how many steps it would take for each buyer to reach a secret value of some arbitrary value, but it's actually a lot simpler than that. And this is slightly unfortunate because both of these parts are actually very susceptible to AI cheaters, which is something that after last day's problem, I thought we had finally gotten to the point of being rid of, but unfortunately this problem is still just too AI friendly. So the price is not the secret number directly, because that would be ridiculous. Like, nobody's going to buy a banana for that much. So the price is instead the ones digit of each of the secret numbers. So for example, if the buyer starts with a secret number of 1, 2, 3, these would be its first 10 prices. The price is the number of bananas that the buyer is offering in exchange for your information about a new hiding spot. But you still don't speak monkey, so you can't negotiate with the buyers directly. The historian understands a bit but cannot negotiate, but can ask another monkey to negotiate on your behalf. Now, the monkey unfortunately is not very intelligent. It is a monkey after all. And the monkey only knows how to sell by looking at the changes in price. The monkey will basically look for a specific sequence of 4 consecutive changes in price and then immediately sell when it sees that sequence. So for example, if we start with 1, 2, 3, you can see in the brackets that these are the associated price changes. The first one doesn't come with a change because there is no previous price to compare to. Looking at this short example, the highest price is 6, so we would like to give the monkey instructions that would make it sell at its optimal time. The first 6 occurs after 2 changes, so we cannot instruct the monkey to sell this early because it just wouldn't be able to. There wouldn't be 4 values yet. So we can try to make it sell here by giving it instructions to sell when it sees -1, -1, 0, +2. After the monkey sees that, it would immediately sell and pick up the 6 bananas from the buyer. Each buyer only wants to buy 1 hiding spot, so once the buyer has made a transaction, the buyer will leave and the monkey will move on to the next buyer. The monkey can also never hear that sequence of price changes from a buyer, and if that happens, the monkey will never sell and that buyer will just not give us any bananas. What's even worse is we can only give the monkey a single sequence of 4 price changes to look for, and we cannot change the sequence between buyers, and we want to get as many bananas as possible given these pretty tight restrictions. Each buyer is going to generate 2,000 secret numbers, and so for each buyer we'll have 2,000 price changes, and so we don't have to look infinitely. We don't have to really do anything too intelligent here. We can literally just loop through. So the first way I thought of approaching this was to brute force every possible sequence and just look through each buyer to find where it first occurs. But then it occurred to me, first of all, that is obviously way too slow. The possible values for each change ranges from -9 to +9, which is a total of 19. And we can see that that gives us a total of 130,000 different possible difference sequences. And given that each buyer has 2,000, and we're looking through a total of about 2,500 buyers, that would give us this many numbers to loop through in the worst case. And obviously it's going to be smaller than this because we're going to quit early when we see our sequence, but this is just ridiculous. And the main reason is just because of this factor, and I realized that we really don't need to do this because we can just scan through each buyer and add to a map that tells us what the worth of each sequence is. You'll notice that the number of possible change sequences is very, very high. In fact, it's high enough that most of them will never be seen at all. And so there's no point in looking at those. We can just look through the buyers and record the sequences that actually do appear. And so we'll do this. We're going to want to obtain the full list of each buyer's prices. So we're going to make that a list. And then for each buyer, rather than just looking at the 2,000th generated number, we want to store all of them. So buyers.append, or rather we'll first make this buyer a list, which contains the ones digit of the first number. And then for each step, we're also going to add the price value, which is that secret number modulo 10 to get the ones digit. And then at the end, we'll add that to the list of buyers. And so here's our example input. We can see that this is not very useful. Let's give a 1, 2, 3 as an example and just print out the first one's first 10 values. We can see that we get the values from this list exactly as expected. And now we can just scan through each buyer and look at each block of 5. Because the changes are because we're looking at sequences of 4 changes, that's the differences between 5 values. So we'll look at each slice of 5 values. So we can do this by, actually, we don't need a list of buyers because we can just process them one at a time. For I in range length buyer would go through each index in the buyer. So for example, if we have a list 1, 2, 3, 4, 5, 6, the index would start from 0 and go up to 5. But of course, we can't start a block of 5 at the end of the array. So at most, we can go up to index 1 in this case, which is the maximum index minus 4. So we can go up to length of buyer minus 4. And then we can get the slice of 5 starting at that point by doing I up to I plus 5. And so we can do A, B, C, D, E equals that. And then the sequence of differences is going to be the second value minus the first, then the third value minus the second, so on and so forth. So that is the difference sequence. And if this sequence is seen, we will buy at the end of the sequence, which gives us E bananas. In order to make sure that we don't look at a different sequence that's already appeared, because if the monkey were looking for that sequence, it would have sold at the first match, then we'll keep track of which diffs we've seen. So, like so. If the sequence has already been seen, we'll skip it. Otherwise, we'll add it to the list of seen sequences. And then we just need to record the increase in price that this sequence would get us. So basically what I'm doing here is, if we were to look for this sequence, the first time it appears, we would get E bananas off of this buyer. And so we'll just keep track of, for each sequence of for each sequence of diffs, what is the total that we would get if we were looking for it? So if this is a case where we would sell here, then sequence to total of that sequence increases by e. Now this initially could be empty, so we'll do if sequence is not in sequence to total, then that equals 0. And so now if we look at that, this tells us a couple of things. For example, if we looked at the sequence 1, 2, minus 4, 4, we'd get 6 bananas. If we looked at the sequence minus 9, 7, minus 6, 7, we'd get 8 bananas. And so that tells us now for each sequence that does actually show up, if we sold at that point, what would we get? In some cases, we would get 0 because sometimes the buyer's price is 0. And note that the size of this is way smaller than the total number of possible sequences because most sequences won't be seen. And so this basically just prevents us from doing a bunch of redundant work. We need to know the maximum possible number of bananas we can get, which we can just do by taking the max of the values of the dictionary. And that gives us... That is notably incorrect. Oh yeah, I forgot. It's because the part 2 test case is different. Yeah, there's nothing wrong with my code. I just forgot to change the test case. Yeah, so this gives us our answer for part 2. It does take a bit of time to run, but we do get our answer in the end. Now I want to discuss some optimizations because as you can see this is taking a while. So I'm first going to do the part 2 optimizations because they actually matter a bit more and they're a bit more interesting. And then I'll look through part 1 and see if we can find some way to use the bitwise operations here. So looking at part 2, we note that we're doing a lot of repetition here because each time we're picking up a new slice, but most of these values, in fact the first 4 of these values, were already in the previous slice. We're also storing a list of these 2000 values, but really we only need to look at each block of 5 at a time. So let's try to do this in real time. And so we're going to store the last 4 values. So initially buyer is just going to be this, and we'll basically try moving all of this into this block so we only need to keep track of 5 values at a time. Now removing elements from the start of a list is not very efficient, although it scales with the size of the list, so if the list only has 5 values, it doesn't really matter. But we'll optimize this incrementally. So first we're going to move the scene set up, and then for each range we're going to do this. Now if the length of the buyer array is greater than or equal to 5, that means that we have a block we can look at. This basically skips over the first 4 values. We could also do that by creating a separate loop of length 4 and then one of length 1996, but that isn't really helpful. So if the buyer array has at least 5 values, then that means that we're going to look at our block. And then we're basically going to move all of this up. And finally, we're going to pop the leftmost value out of the buyer array because that one will no longer be looked at. When we add the next number to the buyer array, we're going to only be looking at the last 5, so the first one is obsolete. And this case would be because I forgot to account for the continue. We can move that all the way up here because after we unpack the buyer array, we don't need to worry about modifying it. Okay, so that gives us our answer for part 1. Part 2. But this is not really going to be all that much faster. Instead, what we can potentially do is look at the current block of 5, but also keep track of the current block of 4 differences. So what we can do here is we can store our differences array. And what we can do here is the first time we reach the buyers, we're going to compute all of the differences. So actually, let's do this. We only need to now keep track of the previous buyer number so that we can, the previous price so that we can add it to the differences. So previous is equal to num mod 10. And now num equals step num. So we will take a look at previous minus num mod 10. And that's going to be this difference. So we can add that to the differences. And so initially when num is at the start, we only have one price and no differences. Then upon the first iteration, we'll get the next price and add it to our list of differences, and this will give us our first difference. And then we update the previous value to num mod 10. And so now we don't need to even keep track of the prices, and now we only process if the length of the differences is at least 4. And we'll modify it by popping off the first value again. And now our sequence is just equal to diffs. Except you cannot use a list as a key, or insert it into a set because hashing issues. So we will have to turn it into a tuple. And E is not defined here, but that is just equal to the current price, which we got here from num mod 10. If we want to make it a bit clearer and not use a confusing variable name called previous, we can just use num mod 10. Yeah, right, that one is because I put them out of order. Okay, sorry. Yeah, that gives us our answer for part 2. And based on the time it's taking, it seems like that really doesn't save all that much time either. Okay, I think today might just be a case of Python is slow. I don't think there's really too much of a way I can optimize this further. But yeah, so that's an optimized way of doing this, but given that it's a bit confusing, let me just go back to what we had previously. It seems to have taken basically the same amount of time. Yeah, an interesting exercise nonetheless, but not really too worth it, especially because it made the code a lot more confusing. So anyway, this solves part 2. Now, like I stated earlier, I do want to see if there's a more efficient way to do part 1 here, involving avoiding looping 2,000 times. In part 2, because we need all of these numbers, skipping the looping is impossible, but I do want to see if it's possible for part 1. So I've reverted the code back to where we were at part 1, and now let's see what we can change here. So in case you're interested in following along with this and not familiar with bitwise operators, let me explain what I meant by a couple of the things I said earlier. So I've already explained binary and what bitwise operations do, but the 3 we need here are left shift, right shift, and the AND operator. So left shifting takes the number and shifts its bits to the left, replacing the empty space in the right with zeros. So for example, if we were to shift the number 13 in base 10 to the left by 2, we would get 1300. Basically, we would be multiplying by 10 to the power of 2. Similarly, if we left shift a value by 3 places in base 2, we're multiplying it by 2 to the power of 3, which equals 8. So for example, if I look at the number 101, which is 5 in base 2, if we left shift that by 3, we get 10100, 0, which is equal to 32 plus 8, which equals 40, which is 5 times 8 as expected. So we'll note that one of the operations required getting number times 64. Because 64 is 2 to the power of 6, that's just equal to num left shift 6. Right shift, as expected, just shifts the bits to the right, cutting off the ones that are removed. So for example, if we were to right shift 40 by 2, we would basically be dividing it by 2 to the power of 2, which is 4. So 40 in base 2 is 101000. If we right shift it by 2, we get rid of the last 2 bits, which gives us 1010, which is equal to 10 because it's 2 plus 8, which is 40 divided by 4 as expected. Note that this is also floor division, which is required for the problem. If there are ones here, then normally dividing by 2 would leave these as a decimal, but they get cut off instead. Finally, the bitwise AND operator, it works very much like the XOR operator, but even simpler. If we look at 11 and 13, for example, we just line up the bits and then just calculate the AND of each value. And as the name implies, the AND operator only returns true if both of its values are true. So 11 and 13 would give us 9. So I said that we could replace this with AND, but only because this is a power of 2. And the reason I say that is because when we take the modulo by a number, it's the remainder when dividing by that number. And so for example, Let's go back to base 10 just to make things easier to understand. If we look at the number 13,796 and modulo 1000, then we get 796, and you'll notice that's the same as taking the last three digits. And this is no coincidence, because if we divide by 1000, then we get 13, remainder 796. And so this part would be the floor division part. This part is the remainder, which we get from the modulo operator. Now in base 2, if we were to take 101001 and take that modulo 10000, which is equivalent to 12481632, 41 modulo 124816, we expect to get a value of 9, because 41 divided by 16 is equal to 2 remainder 9, because it's 32 plus 9. And we can see here that if we cut off the first 2 bits and only take the last 4 bits, we get 1001, which is equal to 9. And so this works exactly as expected. And so because we're taking modulo 2 to the power of 24, we are basically just keeping the last 24 bits. This here is equal to 2 to the power of 4, and we just kept the last 4 bits. If we're just keeping the last 24 bits, what that means is we are basically taking the number bitwise and 24 ones. Because if we line up the 24 ones and then put the digits of the number, then if the number is within the bounds, we only get that. Everything else is 0 because the number implicitly has zeros to the left. And if our number is longer than the 24 bits, like this for example, then we cut off everything before the last 24 bits. And so whenever we have modulo 2 to the power of n, it's the same thing as and 2 to the power of n minus 1, like so. So let's see what that means here. (2048) is 2 to the power of 11. So that would be left shift by 11. And then here that would be and 24 ones. Now, I'm not going to bother typing that out because an easier way to represent that is in hexadecimal, which is base 16. Converting between base 2 and base 16 is fairly easy because they're 16 as a power of 2. Just like in base 10, you can represent each place value increases by 16 times when we move to the left, and the digits we can use are 0 through 9, and then A through F. And so each block of 4 bits can be represented as one hexadecimal digit. So for example, 1101 is equal to 13, which is represented as the hexadecimal digit C. And so the Boolean value 11010111 is equal to the hexadecimal value of C7. We can see this here. 11010111 is equal to 215, and 0x C7 is equal to, sorry, it's D7. 0x D7 is equal to the same. What that means is if we have 24 ones, we can just represent it as 6 Fs. Now granted, that's also, you could also say that's unnecessary because you could just say the modulus is equal to 2 to the power of 24 minus 1. But, you know, might as well take the opportunity to introduce a new thing. And so this will also give us our answer for part 1, but it won't really be too much faster. I am curious if it is at all faster though. That's not helpful. So that takes 1.668 seconds. Okay, so it's not faster. It's probably not slower. That's probably a fluke because bitwise operators should definitely not be slower. But yeah, most likely what's happening is just that Python is not a language where these optimizations matter. Now, what I did want to look into was whether or not we can skip this check here, like skip this loop and compress this directly. I wonder if we can reduce this. Nope, that gives us the wrong answer. And honestly, I think the answer here is unfortunately no. I don't think there's any way to optimize this. Because it's mostly because of this right shift. When we right shift, if we don't clip off the leftmost bits, then they'll end up back in range when we do the right shift. So yeah, I don't actually believe there's any way to optimize this more than just the trivial method. I'm honestly kind of surprised that on day 22, we still have a problem where the solution is to just implement it trivially, and there's not just no optimization required, but it seems no optimization even possible. But if I have missed something, which I very likely have, please do let me know in the comments, as I do really want to see if there's a way to make this more elegant than just implement the problem statement directly, which unfortunately is really good for AI cheaters, because today's problem took quite a bit of reading to understand, because there's a lot of flavor text, and even the implementation is obfuscated by having the definitions of mixing and pruning further down. And AI can implement something this trivial really easily. So I'm quite disappointed, but please do let me know if there's an optimization I've missed. Doesn't change the fact that this problem was easy for AI to abuse, but at the very least, if there are optimizations, I would be interested, and that would make this problem a bit more fun for me. But in any case, I hope you enjoyed this video nonetheless. Thank you for watching, and I'll see you again tomorrow.